do now, it is somewhat clear that you are familiar with some properties of gases. We're going to review properties of gases. We're going to compare and contrast them with properties of other states of matter, such as solids and liquids. What we're really going to delve into today are some of the gas laws that show the relationships between different variables we're going to be talking about. You'll be doing a lot of calculations there, which are very, very simple. We will be doing 2 different labs that deal with gas laws. You'll be heating up the gas, cooling it off, and looking at the effect on volume. And then you will be using lighters again. And you will be able to confirm the quantity for the universal gas constant. So you've got 2 cool labs to do in this chapter. Today we're going to review properties of gases as well as introduce some of the gas laws. Most of you have a very high level of understanding of stoichiometry, and we're going to link stoichiometry back to gas laws here. So the first thing that we want to do Hey guys, I turned the recording on and now everybody can see exactly what I'm talking about.
It's all Dean's fault. You just said that because I'm African. That's
Some basic properties of gases, as many of you mentioned already. Solids. Solids are very rigid. Let's refocus. Liquids. Look. Take on the shape of the container. There's ice in there too. Shh. Gases not only take on the shape of the container, but they occupy the entire space of it. You'll see that when you're talking about the volume of a gas, you're really talking about the volume of the container the gas is confined to. We will be looking very carefully at how volume is altered when you alter temperature or pressure of a gas. We'll actually be exploring all of that today. In regard to particle arrangement and particle movement, you can see that clearly here. And you also can see just how much we've learned this year and how it starts to come together. We know water molecules contain 1 oxygen and 2 hydrogens. The hydrogens are in white. You will remember this bent molecular geometry for water molecules. What intermolecular forces link water molecules together? Dipole to dipole, hydrogen bonds and covalent bonds hold the O and H.
London dispersion. German.
LDF. Close. I heard like JPEG and things like that. LDF. London dispersion forces are LDF. No, it's not Lipton.
I know, I got confused.
Oh, okay. In any event, in a solid, you can see that the particles are highly arranged, very little movement. What are in the liquid state? Many of the IMFs have been broken. The particle arrangement is much less. The movement is greater. And then what are in the gaseous state, you can see, as soon as I let you go from the lesson, there you go. Boom, 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 boom. No particle arrangement. Crazy movement. So you've got solid, liquid, and gases. And some examples of solids, liquids, and gases are illustrated here. Yes, group 18, you've got your, let's focus. This is a beautiful picture, and I know it's Valentine's Day. The gases, for example, in the air you have nitrogen, oxygen, carbon dioxide, helium. You very often suck out of balloons at parties because it's fun. Chlorine gas. Your noble gases in group 18. You also are going to want to really keep track of your diatomic gases in this chapter, and we'll come back to those in a bit. Physical properties of gases can best be explained through the kinetic molecular theory. I've got a little video for you to watch here. I'm going to accelerate the video because it's very long, and I'm not sure that you can...
We can handle it.
Yeah.
We can handle it, I promise.
Don't promise something.
If anyone can't handle it,
Yeah.
I doubt.
Oh, I watched this
Oh,
guy.
I've seen
He's
this guy.
German. He made me fail all my tests.
Honestly, he sucks.
He needs a new haircut.
Yeah, I'm
so.
He does.
He looks like the blonde guy from One Direction.
That looks like your hair before
Tyler DeWitt is going to explore a few aspects of the kinetic molecular theory. I better make it louder in here.
That's information maybe from
his finger for some reason.
I think it'll still be easy. Then we're going to talk about a theory that's really scary. Kinetic molecular theory of gases, which is a lot scarier than it sounds, and it gives us some rules for how we can think about gases. And finally, we'll look at a few unique properties of gases that are very different from those of solids or liquids. So let's take a look at kinetic energy for a minute. Kinetic energy.
All right, this we talked about previously. Your solid, your liquid, your gas. You can see the kinetic energy is going to be greater in gases as the velocity of those particles is significantly greater than what you see in a liquid.
Red circles. Particles can be either atoms or they can be molecules.
And now focus on the movement in the gases.
That's just how fast they're zipping around here in this container. So solid, liquid, and gas have increasing amounts of kinetic energy. Gases have the most kinetic energy. They're flying around in there, and they're not connected at all to their neighbors. Now, this is a very superficial representation of what a gas looks like. But often, we're going to want to look at problems and think about gas conceptually in a way that will make it necessary to have some deeper understanding about the gases and how these gas particles behave. We obviously can't see gas, so in the problems that we're going to do later on, we have to have a way to think about it, a way to conceptualize it. So it's useful to set up a series of rules for how we expect gases to behave. We'll make these rules or assumptions, and then we can keep them in mind when we have to solve problems or do calculations. Now, this list of rules is what's called the kinetic molecular theory of gases. Oftentimes it's just referred to as the kinetic theory of gases. And as I said, it's a list of rules, expectations, assumptions of how we expect gases to behave. Now, if a gas follows every single one of these rules, we call it an ideal gas. But in the real world, it's very hard to come up with an example of anything that always follows all the rules. We might want to think there exists something like a perfect student, an ideal student, or an ideal kid, but rarely that's the case. Almost always we find a few exceptions to the rules. And so because of that, it's helpful to think of an ideal gas, but in the real world, none of these gases that we're going to talk about ever follow all the rules all the time. At the end of this unit, we'll look at some particularly bad offenders, gases which break rules more often than others do. And we'll look at certain situations that cause gases to break the rules. For the most part, though, all the gases that we're going to look at now, we're going to assume that they're ideal gases. We're going to assume that they follow all the rules all the time. And for the most part, most of these gases only break the rules a little bit once in a while. So we can safely assume that all the gases we're dealing with follow these rules of the kinetic molecular theory. So let's take a look at what some of the rules of this are. And once again, sometimes it's just referred to as a kinetic theory. I'm going to write down here, kinetic molecular theory. Yeah. So in no particular order, let's take a look at some of the assumptions that we make about gases. Well, here's the first one. Gases consist of very small particles that are far apart relative to their size. This is something that's very difficult to depict visually, and I certainly didn't do a good job of it in the phase diagrams that I just showed you. Gas particles in the picture that I drew you look like they're the size of marbles in a glass jar. This isn't true at all. Gas particles are so tiny that instead of thinking of them as marbles in a glass jar, if the gas particles are the size of marbles, our container would be like the size of a football stadium. So these guys are absolutely tiny, and there's a ton of empty space between them. That's the first thing that we want to keep in mind when we're dealing with gases. Here is a second thing, and this is very important. Gas particles are in constant random motion. We hinted about this earlier with those arrows that I drew, the gases moving around. The moving particles constantly collide with each other and with the walls of the container. So all the time, whenever I have gas in any sort of container, or even if it's just no room, these guys are zipping around, they're bouncing against the walls, and they're bouncing against each other. Now, let's think about those balances a little bit more. There are a variety of ways for things to bounce into each other. And here we say that collisions between gas particles and container walls are elastic collisions. What's an elastic collision? Let's think about two balls of slime. These two balls of slime on either side of me come together, and what's going to happen? They're just going to hit each other and they go, bleh. That means the kinetic energy that both of these guys had got wasted in the collision. These guys were both moving, they came together, and they just kind of went black. And all the kinetic energy, the speed and motion that they had, disappears in the collision. This is like what happens if you chuck an egg against the side of a wall. It hits the wall, and then it just drips down, but the motion that it had, the kinetic energy disappears. That's an inelastic collision. The collision between gas particles and container walls, on the other hand, are elastic collisions. A good way to think about an elastic collision is think about what happens when two red or pink round rubber balls hit each other. They hit and they bounce right off. Or one of those pink rubber balls hits the side of the wall, bam, it bounces right back. The kinetic energy isn't wasted in the collision. This ball hits here and it has the same amount of kinetic energy afterwards that it had when it started. That's the exact kind of collision that gas particles get into. They bang into each other and they just fly right apart, or they hit the side of a container wall and they just bounce right off it. So whenever you think about gas particles colliding, you always want to keep in mind the idea of elastic collisions. Additionally, we can say that there are no forces of attraction or repulsion between gas particles. Some particles, like water molecules, kind of like each other, and so almost like weak little magnets, they tend to attract. Other particles, two particles that have the same charge, don't like each other. They're sort of afraid of each other, and so they're going to repel. They don't want to get anywhere near each other. What this law is saying, when we say there are no forces of attraction or repulsion between gas particles, what we mean is that gases are flying around and they're not going to start clumping together because they're attracted to each other. That doesn't happen. There's not that attraction. Likewise, let's assume that two gas particles are passing each other. They're just going to fly right by. If they repelled each other, zoom, they hit out that way when they get close. That doesn't happen. They don't repel each other, and they don't attract each other either. Lastly, here's what I think is probably the most important thing to keep in mind when we're talking about the kinetic theory of gas. And that's that the average kinetic energy of gas particles depends on the temperature of the gas. The hotter it is, the faster they move. So remember that. Hotter for gas movement equals faster.
And we'll delve into that quite a bit.
Is that why when you make like tea or something and like the steam sounds like that really high pitch?
That's why I went so fast.
Like going fast.
Yes.
I don't think so.
Yes.
Yeah, what doesn't make that noise?
All right. In regard to the kinetic molecular theory, a lot of what he said is listed in your notes. You know, gases are made up of very small particles that move in a random straight line fashion. He mentioned the fact that they are dimensionless points, so they're not big like marbles as he initially depicted. You'll see that the average kinetic energy is proportional to the temperature, and you'll see this has to be measured in Kelvin. That'll be critical in this chapter. He talked about elastic collisions as opposed to inelastic collisions. and also that there's no attractive or repulsive forces. He started to allude to the fact that gases really are not ideal. We're not going to deal with that at this level. We're going to really go with the ideal concept, which we'll get into in the next class. Some properties of gases that he didn't mention. Gases have low density compared with liquids and solids. When we did the lab with the pennies and we showed that copper had a density of approximately 9 grams per mil, when you compare gases, they're going to have densities much, much lower, around 1 or even less than 1. Gases are mostly empty space, and because of that, they're highly compressible. So especially in the old age homes where a lot of people need oxygen tanks, you can get a lot of oxygen in that small tank so the people are mobile.
You know how if you like go paintballing or whatever, you have to get that tank of like air? Is that what that is?
You know, I've never paintballed. I know what it is, but I've never gone.
But is it like compressed probably?
What's in the tank?
It is compressed.
Never mind. It's
If it's
compressed.
not compressed, how's it gonna shoot?
Okay, you know, I don't need your stats.
Hey!
I don't need your
So like when you go diving and stuff too, you've got diver's gas, also compressed. There's a lot of gas in that tank, otherwise you're going to be coming up every 3 minutes.
Wait, what is the nitrox air?
That's what you get when you go to the dentist, that sweet air.
No, like when you're diving.
Oh, no, that's... Diver's gas is typically helium and oxygen gas. So you've got oxygen, but you've got another gas in there.
You only use helium for deep diving.
Deep?
Yeah.
Okay.
It's mixed with oxygen.
It's not just straight up helium. Everything over the sea, like the.
They get bored.
It's only under, if you go deeper than 300 meters, you need helium.
Then you do? Why is that?
Like your, what's it called, the cells in your blood, they shrink, and so you need the helium to expand them, or else like your brain's gonna collapse.
You got it.
You have impressed.
The variables that we're going to look at in this chapter include volume, abbreviated capital V. This is going to be critical for success on your quiz. We know volume is the space that matter occupies. We'll typically be doing measurements in mils or liters. You absolutely positively need to know that 1 liter is 1,000 mils. That's not something I'll give you. You should know that at this stage of the game. We already talked about the fact that gases are essentially dimensionless points, so when you're talking about volume, you're really talking about the volume of the container. A second variable we're going to look at is temperature, abbreviated with a capital T. Be careful, lowercase t is time. And this we're going to have to use Kelvin for. Typically we make measurements in degrees Celsius. In this country we do a lot in Fahrenheit because we've been unable to adopt the metric system, and we can't seem to adapt to it, even though it's a much better system, especially for cooking. We still go back to cups and ounces and teaspoons, and it's a much more difficult conversion.
So, like in Britain, is an inch worm a centimeter worm?
It,
Like,
is what?
do they know what an inch is?
Actually, over in Europe, they do all their measurements in the metric system. So, for example, when I worked in a lab up at Hopkins, we had several people there who were from Germany, and they wanted to get driver's licenses in this country, and they only know their height in centimeters, and they know their weight in kilos or kilometers. No, not kilometers, kilograms. Kilometers would be a bit much. So in kilos and kilograms, and they don't know how tall they are in inches and feet and how much they weigh in pounds. They solely use the metric system over there. We've just been slow to it. It's actually a much better system, and if we actually used it for cooking, it'd be a lot easier. Instead, you have to think, okay, how many teaspoons in this, and it's much more difficult here. In any event, if you have a foreign exchange student staying with you and they want to go get a driver's license, just remember 1 inch is 2.54 centimeters, and you'll get them converted right away. In any event,
I thought it was 2.6.
2.54.
Which rounds down to 2.5.
I understand. Thanks.
If you watch, for example, we watch a lot of tennis in our house, and when they're in America, they do all the speeds in miles per hour. You can look at serve speed in miles per hour, but when they're over on the other side of the world, everything's done in kilometers per hour. So you just multiply that by 3/5 to convert.
Isn't like an average professional serve like 110 or something?
It varies for men and women, and it also depends on what first serve is versus second serve. But let's not get away from gases. All right, when you want to convert,
Isn't the serve like
from degrees Celsius to Kelvin, it's very, very easy. You simply add 273.15. I'm not going to give you that number, and it is critical, critical, critical. Right, Devin?
Yes.
Absolutely. So, if I gave you a temperature of 22.00 degrees Celsius, what would the temperature be in Kelvin?
293.15.
295.15, which you got by adding 22 to 273.15.
What if it's like a negative degrees, and then like do you
still
still
add.
add?
Yeah.
Okay. Wait, that was a dumb question.
No, it's not. But the other thing is if you're in Kelvin and you want to go to degrees Celsius, then you subtract 273. You'll see both versions today. Another variable we're going to look at is pressure. So let's put this all into perspective here. Variables we're going to be focusing on include volume. We'll either do liters or milliliters. Temperature. You have got to do Kelvin or you're going to crash and burn. You will not pass the quiz if you don't play Kelvin. Pressure. There are many units of pressure. You've got atmospheres, kPa, millimeters of mercury, torr. Those are pretty much the ones we're going to be using. But again, over in our country, we use pounds per square inch, bicycle, car tires, etc. And pressure is equal to force per unit area. So Devin, are you going out for Valentine's Day?
Yeah, after football practice.
Awesome. So, let's say that you're going to pick up your girlfriend and you're going dancing. And that's the spiky heel. Dancing.
D is for girl.
Here's the spiky heel that she's wearing. Look at the area. That area is really, really small, right?
Yes.
Yes. So when she steps on your foot, you may still love her to death, but your foot may never be the same because the pressure on your foot's going to be huge. Now, let's say you decide to go up north because you want to freeze your butt up.
Why can't she wear wedges?
Then it wouldn't hurt so
I know,
much.
that's what I'm saying.
Punishment.
She doesn't have wedges.
She's not that tall. She's going to wear heels.
But Devin doesn't
But you
dance.
can get really high wedges like with the platform.
Alrighty.
It's a snowshoe.
It's a snowshoe. Not a very good one.
Didn't you major in art?
Yeah, you'd never know it.
I think minored in art.
If you use it, if you don't use it, you lose it. Here's your little foot.
That's a foot. That's a paw. That's a
Oh, stop it. What's happened to the area of the snowshoe? It's huge.
No, the pressure is the same, it's just nowhere. It's
So the pressure is less the larger the area. That's why when you go up north, how many of you ever have gone up north and truly worn snowshoes, not boots? Where'd you go? Idaho? There's snow in Idaho?
I know, it was actually really good skiing, honestly.
I thought there were potatoes. You went to Alaska would be a perfect place.
I've been to
But isn't the
Alaska.
pressure the same as Johannesburg?
You know, I lived in Pennsylvania for 8 years and I never wore a snowshoe.
I lived in New York for 18. I never wore a snowshoe either.
I saw that.
If you increase the area, the pressure is less.
How is the pressure? Okay, so if you put five pounds, right, in on top of like.
You're talking about force. Hang on. Now, when babies are little and they want to sleep on your shoulder, it's fine. They don't weigh that much. You don't drop them in the middle of the night. That's why you have carpet. All right.
That was me.
So the babies have a low mass, they have a low force, very little pressure exerted. But babies get bigger and bigger and bigger. And when your 8-year-old crawls into bed and wants to sleep on top of you, the pressure is just way too much.
Tell them to get out.
Just you wait, 15 years from now. I didn't even hear that. In any event, pressure and area. Pressure and area are inversely related. As one increases, the other decreases. Pressure and force are directly related. Force is equal to mass times acceleration. So the greater the mass, the greater the force. The greater the force, the greater the pressure. Alrighty? And another variable that we want to consider is N, which is the amount of substance that is moles, abbreviated MOL. And what we're going to be exploring today is the relationship that exists among these variables. We'll hold off on moles till next time. So we're going to talk a little bit more about pressure. Then we're probably going to have to take a break. And then we're going to look at the relationship between these variables. It's very, very mathy. You're going to be very, very good at it if you remember a few things. All right. We can measure gas pressure very easily. One of the things we'll need to do in both of our labs is we will need to measure atmospheric pressure. And you can measure atmospheric pressure with a barometer. You actually can go right online to weather. And you can pull up barometric pressure, which is measured at the airport. Alternatively, some of our weather people down the end of the hall have barometers in their classroom, and they'll let us know what barometric pressure is. A barometer, very simply, is a bucket with mercury in it, an upside-down glass tube. The atmosphere exerts pressure on the mercury, and the mercury will rise. You will measure the height of the mercury. That will be atmospheric pressure. So a barometer is used to measure atmospheric pressure. Now, a lot of calculations, measurements, etc. are done at STP. And STP stands for standard temperature and pressure. The temperature is 0 degrees Celsius and the pressure is 1 atmosphere. STP is something you will want to be familiar with. A manometer is a device used to measure gas pressure when the gas is confined in a container. For example, bike tires, car tires, etc. Some of you know how to measure the pressure. You're using a manometer. Awesome. The other thing you just want to get comfortable with, and you'll be very good at this because you're very, very good with the factor label method, is there are many, many, many different units of pressure. Some of the equivalencies are shown here. They would be provided to you. You don't need to memorize these, so if you need to do an equivalency, I will give you, if you need to do a conversion, I'll give you the equivalency. Let's look at the first one together, and then you'll take a look at the second one. In the first one, we want to convert 803 millimeters of mercury, and we want to go to atmospheres. And the same way we did this back in the first week of school 6 months ago, we can convert from millimeters of mercury to atmospheres very easily. Is there a conversion that has both atmospheres and millimeters of mercury in it? Sure.
But is it mole?
No moles.
We're not doing moles.
1 atmosphere is 760 millimeters of mercury. Factor label method that we've talked about quite a bit already. You've got 803 divided by 760, and you've got 1.06 atmospheres. Pretty cut and dried, don't see an issue there.
We got that from the reference.
Mhm. In the second problem, you have 3.25 kPa, and you want to get to bars. I'm going to put, some of you don't appear to have your notes, I'm going to put the table back up and take a minute to do that conversion.
KPA.
You want to go kPa to bars.
So you have to do KPA to PA to bars.
Right.
Is KPA 1,000 PA?
Yes.
It says that right there.
Yes, it does.
Where?
It says 1 kPa equals 1,000 PA.
I did not look at that. I just got it.
I'm not mad.
Kilopascal. Bars.
I'm not your slave. Well, just because I'm African.
Dean!
He missed it.
He keeps making like oppressive women jokes.
This is on camera.
Doesn't sound that
Oh my god!
How do you know he else hear what he said?
He says I'm not allowed to talk in public. Wait, and then I have to sit here and sew.
I kind of got a hold. So.
Guys, you've really proven today many of the points that I've illustrated.
Not me. What do you mean?
What did we get?
I put so many candies in
But
there.
number one, I got 107,065,596.
Do you have point
I got 107.
Oh, never mind.
Point
Wow.
324, is that what you got?
What?
I multiplied it.
I think Maddie's got it.
My notes read too.
Well, okay, so 3.25
Is your setup right?
3250.
divided by 10.
Oh,
Oh, I missed an O.
Oh, it's 100. Oh,
It would be a 0. I just realized what it is Valentine's Day. You guys have had way too much junk.
Yes, that's the problem.
I had like 4 cookies.
That's why I'm so hyper.
Macro.
I don't have any.
Actually, that's false sugar, just make it hyper. Not real.
Questions here. Very simple conversions. We will revisit conversions in a bit.
It's the hardest part of the chapter.
This is the easiest part of the chapter. We are going to be looking at 3 gas laws today that will be assessed on your quiz the next class period.
Wait. Thursday.
Very, very straightforward. You'll be very successful here if you can focus. Let's do at least one now. We may need a break to make it through.
5
Say it again.
There are 5 gas.
There's a whole bunch, but we're going to start small. I think the trickiest part is once you see them all is trying to figure out what to use when. And we'll go over some strategies to be successful there. The first gas law we want to look at is Boyles' law for Robert Boyle, who is looking at the relationship between volume and pressure of a gas. What he found is that when the pressure is increased, the volume is decreased. Alternatively, if you decrease the volume, you increase the pressure. Think about bubble wrap. You put your finger on that bubble wrap and you've decreased the volume. When you decrease the volume, the pressure gets greater and greater until it pops. Think about a syringe. When you push down on the plunger, the pressure is increasing, the volume of the gas will decrease. We can look at Boyles' law a couple different ways. For example, this is a little hard to follow. Here's your temperature gauge. You want to maintain constant temperature. Here's the pressure gauge. So when the piston is going down, the pressure is increasing. As the pressure increases, the volume decreases to 2 liters. As the pressure is decreasing, the volume increases, and you can see this inverse or indirect relationship. As the pressure increases, the volume decreases. This is an inverse relationship. It's important to understand the relationship to be successful with these types of problems.
What's the blue thing on the side? No, the
It's probably insulated. So as I said, if you increase pressure, you decrease volume, and vice versa. When you want to show an inverse relationship, you multiply the 2 variables. The product of pressure times volume is equal to some constant K. So if you have pressure and volume under one set of conditions, you can compare them to a second set of conditions because they're both equal to K. Your formula here is P1V1 is equal to P2V2. Graphically, you've seen it already. Let's walk through a few examples here. I also want to point out several tricks as well as the relationship between these 2 variables. This will make you more likely to be successful on your quiz or any subsequent assessment. In the first example, let me backtrack for a sec. It says helium gas occupies 4 liters of space, the volume, and exerts a pressure of 2 atmospheres. If the pressure is increased to 6 atmospheres, we want to know the volume. So we have 2 sets of conditions. Yes? What? No. So let's take it slow and see what happened. The relationship is inverse. So the pressure tripled. The volume has to decrease by a factor of 3. Well, it would be 1.33 liters, but I guess you're thinking, let's take a look at this, guys.
Wait, I'm confused.
I know.
Where did they take from? Because
The first, because she's multiplying 3 times 6, which I don't get either.
Yeah, I
But
don't
we'll
get
figure it out soon.
okay.
Volume 1
Oh, you just put a dot in
is 4 liters. P1 is 2 atmospheres. Now the pressure is increased to 6 atmospheres. We want to know the volume under the second set of conditions. We can see that the pressure increased by a factor of 3. So the volume has to do the opposite, that is decreased by a factor of 3. So 4/3 is 1 1/3 is 1.33 liters, but you can do it plug and chug style. You've got P1V1 is equal to P2V2. You're solving for V2, which means you're going to divide both sides by P2. Now V2 is equal to P1 V1 over P2. 1/3 of 4 is 1.33 liters. And your answer is consistent. The pressure increased. The volume is going to decrease. Please stop it. You're going to break something. Does that make sense? Yes?
Yes.
Yes.
Notice that I manipulated variables before I plugged in my quantities. Notice that I have quantities here rather than numbers alone. Why don't you take a minute without yakking to try and do number 2? Today's Valentine's Day. You made such a nice gift.
It's time to get part 2 of it. How it's on video.
Is it 4?
Couple things we want to look at here. I'd also like to show something to many of you who are hoping to go to AP Chemistry next year. In AP Chemistry, a lot of the problems are done without a calculator. So what you're looking at here, you can see when you go from 2 to 1/4 of a mil, you're decreasing by a factor of 8. So this you would be increasing by a factor of 8. 8 times a half is 4. Alternatively, you can write your formula out, manipulate your variables, plug and chug, and instead of putting 0.5 in, I very often will work in fractions because I can see that half of 2 is 1, divided by 1/4 is 4. So you can go about it a lot of different ways to be successful.
Isn't the measurement supposed to be ounces?
Say it again?
Wouldn't it be ATM?
Yeah, ATM.
Yes, I have the wrong unit. You are correct. Your mils cancel and your unit is ATM. Thank you. Sloppy, sloppy. -1.
Does that mean all of us get a +1 on our next quiz?
Well, maybe if the behavior had been better, I would.
We got through the whole lesson.
But I already subtracted 5 points for behavior, so you guys still owe me 4. Let's see if it gets better.
Devin's gone, so we probably will.
It wasn't even him this year.
That was you.
No, it was you, honey.
Yeah, it was
All right. Questions here.
Is that a woman's right?
So you've got ATM here.
It's not acceptable.
Okay. I think the best thing to do, we've still got Charles' Law and Amonton's Law. They're both very, very simple with one major key piece to be successful. And then at the end, I do want to review the nuclear with you. I think what we will do is we will take a 5-minute, no work, no stress, no nothing break. All right? What you should have so far is a basic understanding of properties of gases, the kinetic molecular theory, and the fact that we're looking at the relationship between variables.